Thank you, Dr. Bose. Uh, a very warm welcome to all the participants and also Dr. Dev, who is sparing his valuable time for us. And really, I'm so happy. Rather, I feel honored to welcome Dr. Rajdeep Dev, Senior Research Scientist, ETH Zurich, Switzerland, for sharing his views on numerical modeling of flow mechanics problems in fractured reservoir. So this is, and I'm very happy that we are organizing first time international webinar is organized in our department. So, and very good afternoon to all of you, all my students, my esteemed colleagues. I'll not waste much time. I'll request Dr. Indrajit Bose to introduce Dr. Dev. Thank you.
Okay. Thank you, Dr. Chakraborty. I'm taking off from there. As I am privileged to have with us as our resource person today, Dr. Rajdeep Dev, Senior Research Scientist of the Laboratory of Physical Chemistry, ETH Zurich in Switzerland. Dr. Dev has had an extremely distinguished tenure in various academic positions. He completed his PhD from the Institute of Fluid Dynamics, ETH Zurich, his MSc from the Swiss Federal Institute of Technology, and he graduated from IIT Guwahati. Dr. Dev's doctoral research work was on the numerical modeling of fluid injection-induced shear failure, tensile opening, and flow mechanics coupling. He has 6 journal publications, several conference publications, and apart from his distinguished tenure in academics, it may interest all of you to know that Dr. Dev is also a long-distance runner, an ace swimmer, and he's interested in windsurfing and hiking in high altitudes. So over to Dr. Dev for the session.
Thank you, sir. Thank you, Dr. Indrajit Bose, and thank you, Sujitra ma'am, for introducing me. And thanks, my friend, Dr. Anup Thander, for giving me this opportunity to present my work in GNIT. I would like now start my presentation. So Anup, I can get into my screen now, huh? I can start my share now. Okay. I'd like to share the content. So, is that Anup, you need to first stop your sharing so that I can share my screen?
Okay. Okay, that's the please.
Yeah. Can share your screen. I'd like to access. Can you see my screen? No.
No, sir, the screen is not yet visible.
Oh, why it's not working?
Is it a PowerPoint? So then you can open the PowerPoint separately, and then it will show it on the. It can be shared easily then.
Okay.
Just
okay.
open it.
No, it's it's a keynote presentation.
Okay.
Means Mac, but I think generally there should be an option. Okay. Let me see quickly why it's not.
If you just open it on your screen separately, then you'll be able to access it from here.
Yeah, I opened it my screen. Yeah.
Okay. Then you click on the present now and a window over there.
Yeah, just a minute. Generally, I use the Zoom, so there it is easy, but here it's I don't know.
Yes.
Side. No. So the thing is that first of all, it's asking me present. When I ask for present my window, your entire screen.
No, you don't
So,
click on entire screen. Click on a window. The option below that, a window.
oh, okay.
Yeah.
The window.
You click
Okay.
that, you will get it,
Uh-huh.
and then you can
Oh,
click on it
okay.
and share.
Thanks. Yeah, thank you.
Yeah,
Thank you so much.
yeah. Right.
Oh, can't share. System preference. Okay, just a minute. I have to get the permission for system.
You
Yeah.
just
Okay. Yeah.
enable the permissions, it will come through.
Yeah, I have to quit now quickly just after getting the permission, and I'm joining quickly.
Okay, fine. Yes, it's clearly visible. You got it. Yeah, it's there now. Yes, Dr. Dev, we can see, we were able to see the presentation. You can upload that. Your microphone is off. Yeah, it's visible.
Okay. Now can you hear me?
Yeah. Yes, we can hear you. Right.
Okay.
Right.
Thank you so much. Sorry for this problem. Yeah. Now
No,
I'm
that's all right.
my
Fine.
presentation. Okay. So hello everyone. Welcome to my presentation. And the topic is numerical modeling of flow mechanics problem in fractured reservoir. I did this work in the Institute of Fluid Dynamics during my PhD, and I also guided some other students later for in this work. So I've done this work with Professor Patrick Kenny in the Institute of Fluid Dynamics, ETH Zurich. So first of all, I will give you a brief motivation of my talk. The motivation for working on fractured reservoir is because there are a lot of processes and operations which are related to fractured reservoir. And for example, an obvious thing that you all know is oil and gas extraction projects. There is called shale gas projects, which are very famous now in USA. This is serving a lot of energy resource for in US and also in different parts in India. So in the shale gas projects, what's being done is you inject the fluid at very high pressure or water at very high pressure under the ground, and it will crack the rocks there. And there is a lot of gases which are stored in this pores of the rock. And then you extract this gas, this natural gas, and you use it as your fuel. A third thing is geothermal systems that is now it's a more green alternative to these two sources. And where what is being done is that the rock is very hot under the ground, like 3-4 kilometers under the ground. Rock is very hot in different places, not everywhere, but some places. And what you do is that you inject the fluid at very high pressure again, and you break down the rocks there, kind of create some fractures there. And as the water or fluid flows through these fractures, they extract the heat from the rock, and they're collected in another well outside. And this can be, the heat is so much that water is converted into steam. So if you collect the steam outside, you can get energy from this, like electrical energy, or if you just can get a hot water, which can be used for thermal energy source or some heating process in different parts of the world. Then there are a lot of other processes, mining, open pit, reservoir operations. And what a typical problem with this kind of process is that often or sometimes these industrial operations can lead to some kind of earthquakes. So one very famous earthquake happened in India in 60s and 70s, where there is something called Koyna Reservoir in Maharashtra, where in that case there's a dam operations, and you store the large scale water in the dam, This lead to a lot of change in the underground geological system, and it lead to small scale earthquake there. Also, shale gas projects in USA has caused a lot of small scale earthquakes, a lot of local problems there, local risk assessment needed there. So therefore, it's not that large scale, like causing a life threatening, although, but it will definitely damaging in the local surrounding, and so you need to be careful. And similarly, geothermal process in Switzerland, Basel, the geothermal plant was caused an earthquake of around 3.4 magnitude, which lead to local damages around the household neighborhoods, and therefore the plant was shut down. So geothermal seems to be a very green alternative to these resources, but geothermal is also prone to this kind of earthquakes. So before going for reservoir operations, we need to get some kind of understanding of the underground reservoir. But underground reservoir is not so much easily accessible to us. It has a lot of complicated physics there, and we need to therefore comes the task of numerical modeling and simulation. So first understand by computational models what are the problems, and then based on that take some decisions. That was the risk part of the underground reservoir operation. But also there is another reason where underground reservoir operation need to be modeled, and that is more about the engineering application. So what is done is that, as I discussed with you, you inject the fluid at high pressure, it will lead to opening of the fractures. And how this opening happens, there can be two ways. One is the fractures are shearing over each other, and that is actually the cause of small earthquakes also, but this is also important in creating the hydro aperture there under the ground. The more the aperture is created, the more the water flow through this system, or more you can extract the natural gas from this system, oil extraction can be possible. So therefore mass transfer is increased. So definitely one engineering requirement for underground operation is to increase the hydraulic aperture. And there are two modes. So one is, as I saw here, because by injecting water fluid, you increase some kind of fluid pressure, it will lead to some shear failure. I will come to it in detail in later, and that will cause some kind of opening. Another is the pressure is so high that it is beyond the tensile strength of the fracture, and that will lead to an also opening of the aperture. So these two modes of operations by which fractures are created or fractures become more engineering viable to us, but so therefore we need to do some modeling and understanding of this phenomena. Okay. So with this motivation, now I'm going into my topic, which is the numerical methods, how the numerical methods applied in these fractured reservoirs. But before going to the numerical methods, let's give you a brief introduction of the physics of the problem. So physics of the problem is easy. Basically, a simple governing equations work here for the mechanics problem particularly, which is divergence of stress equal to any acceleration term under the ground. What I mean by is that there is a rock under the ground is under stress because of the geological processes, and there can be the volume force there. Volume force can be because of the gravity or other reasons, and this need to be balanced by if any perturbations happen, this need to be balanced by the acceleration term. Now this is the continuum part of the domain. That means the reservoir, rock reservoir, but there is also fractures under the reservoir. The fractures are a discontinua into the system. It creates some kind of openings, where the rock strength is low there. So fractures and faults both causes this thing. So rock strength is low on the fractures. So we need additional modeling or additional understanding of the fracture. What happened in the fracture? Over the fracture, there can be shear or tensile failure happen. And on each fracture, there is a maximum strength of the fracture available. What this strength is, this strength can be because of the local compressive reason. That means fracture is under compression. But if and because fracture is under compression, and also over the fracture, there is some kind of shearing force always applied. If you remember your simple friction class, that a force parallel to the surface will try to push the surface, but friction is stopping it because of the normal force that is applied there. But there is a maximum limit to that, as we know, like static friction and dynamic friction is limited by the applied compressive force or applied normal force on the fracture or on any surface. So if the applied shear force exceed that limit, then there will be shear failure happening. So there is some kind of force constraint on the fracture. So overall, unless this force constraint comes up into the picture, the fracture is also a part of the domain. You can just consider fracture doesn't exist. You can just solve the problem above divergence of stress equal to acceleration term. But once this factor comes up, once your applied stresses in the boundaries of the system leading to the issue where shear stress on the fracture surface exceeding the maximum limit of it over it, then you get some shear failure, and then you need to consider that fact. So this shear stress, as I said, depend on the boundary conditions and the material properties of the rock. Material properties are usually, you can define through two material properties most easily. One is called, as you know, maybe knowing it, Young modulus and a Poisson ratio, or you can look into them as shear modulus and Lame constant. It's also a bulk modulus. So these are all material properties. I'm not going to the detail, just quickly explaining. And then there is this maximum criteria of the force, which is, as I said, governed by the applied compressive force on the fracture, fluid pressure locally at the fracture, and the friction criteria. So with these things, now we are moving forward. We are taking one assumption in this problem. The assumption is that problem is always under mechanical equilibrium. This assumption is why we could take this assumption is that, well, it is not always valid when you are having a large scale earthquake, like for example what happened in our part of the world, Assam and Gujarat and what. There you cannot apply this logic because the acceleration time is so high. That's why you are having so much shaking of the ground. But when the acceleration or when the earthquakes are governed by the underground pore pressure, fluid pressure, then its time scale is dependent on the fluid pressure, and that correspond to that time scale. The mechanical problem's time scale is so high, so small, that we can assume the problem is under equilibrium, mechanical equilibrium. And only when we see this kind of shear failure criteria comes up, we have to solve an additional problem. Otherwise, we take the problem as equilibrium. Now another factor comes up: how to model this shear stress term. And shear stress, a simple approximation in shear stress is linear elastic relation. So that means shear stress is linearly dependent on strain terms. And as I said, deviatoric and volumetric, these are the two parts of the strain term. One is called deviatoric strain term, a total strain term, and there is volumetric strain terms. So this shear stress is linearly related to using this criteria. The shear stress is linearly related to the strain term. Basically, you represent the displacement in the domain. So once we can calculate the displacement from this equation, we can estimate the stress forces. And whenever we come to the shear failure, as I discussed, we have to consider additional force constraint, and this force constraint is the forces on the segment become equal to some kind of friction limited tensile shear stress. So with these things, now I'm going into the numerics of the problem. And the first numerical part is extended finite volume method that we have developed in Institute of Fluid Dynamics during my research project. And generally, you have known, generally most of the time finite element methods are used to deal with this kind of problems for mechanics problem. But since we are dealing with both flow and mechanics problem together, we thought, because flow problem is always very nicely governed by finite volume method. I'll come to the detail of the method later. So that's why we are also solving the mechanics problem here using finite volume method. So what it looks like, usually a domain, if you look into the system, underground domain will have a lot of fractures. This is a simple representation, a cartoon representation of the fracture embedded in this rock domain. And now what we have to do is that we have to then there are two approaches to it. A computationally expensive approach will be to resolve the grids around every fracture. And if we resolve the grid around every fracture, based on that we develop our numerics. But that is computationally more expensive, and there are a lot of fractures they are under the ground. If you try to resolve the grids around every fracture, it will be the machine itself will take a lot of effort. So alternate approach is to use a method which is called fracture embedded in a damage matrix. what it is that you consider the domain just as a simple simple structured grid. So just use a structured grid where the domain is discrete into small segments, and the fractures which are present as a discontinuity in this small segment need to be somehow taken into consideration when you are going to solve for the problem. So I am now focusing into a small degree of freedom or small segment of this domain. And if we look into this small segment, what it will store in this particular setup is that on the 4 nodes there, it will store the displacement solutions. And on the fracture, because as we discussed, the fracture can cause shear or tensile failure. That means there can be some additional displacement on the fractures. So we need to store it as something called shear slip or tensile opening. Now, this is our basis interaction region. What I mean by is that this is the smallest segment or smallest degree of freedom of our system. For the matrix, this is the degrees of freedoms are given by this each of the terms u1, u2, u3, u4. These are the matrix displacement nodes. And for the fracture, we consider the fracture's degree of freedom only when it encounters or the part of the fracture which encounters this small neighborhood segment of the four matrix nodes. We consider them as their degree of freedom. Okay. Quickly, before now going to these details, let me give you a finite volume method. So what is the finite volume method exactly? In the finite volume method, what we'll do is that let's now focus on one of the segment of the fracture, on the matrix node. And for each of this segment, we need to solve this equation. As we discussed, divergence of stress plus force equal to 0. So what is done is that on a finite segment, on a finite volume segment, it is integrated over that segment. And then we can use Gauss divergence criteria, And then we can use Gauss divergence criteria to convert this divergence of stress into an area integral. And once it converts to the area integral, that means it's equivalent to a stress into area is equivalent to flux, force. So it's equivalent to a force flux on the boundaries of each segment. I'm going back. And now we have to calculate this force flux on the boundaries. So in order to calculate this force flux on the boundaries, we need to know some additional, because force flux, because as we remember, the stress term is dependent on a strain, and strain is nothing but a function of gradient of displacement. So we need to calculate the gradient somehow on this boundaries. And in order to calculate that, we need to take the neighboring nodes of all of each of the finite volume segment. Now what is done is that on each of this finite volume segment, here is the thing. So we introduce a basis function, which is, it can be varying, it can be a polynomial basis function, but here we are using just simple bilinear basis function. And for each of this basis function, its extended region is in the neighboring 8 nodes for the segment, with it becoming 0 on all these segments, on all these boundaries, and becoming 1 in this particular segment. So our assumption is that our displacement solution is a linear combination of all these basis functions. Now we have to do if we have a look into the sub part of this basis function. This is as why I said previously, it's a basis interaction region, because each on this segment, on this sub 4 neighboring segment, the 4 basis functions interacts here. So correspond to each of these 4 neighboring nodes, and each of them, if we look into the detail, the basis functions will look like this. There's 1 for each of the segment and 0 in all neighboring segments. This is typically used in finite element, but here we are also using this concept in the finite volumes context. Once we know these basis functions, that means we know the gradient along this line. And if you know the gradient along this boundaries, we can calculate the force flux from that. Now comes an additional complexity when comes the fracture. When the fracture is present into the system, it will lead to some additional discontinuity. As I discussed, you cannot no longer use a continuum approximation for the displacement field here, because along the fracture there happens additional shear slip or tensile opening. That need to be taken into consideration when you're gonna solve for force flux now, because otherwise what will happen is that if we take a simple approximation, if we take the gradient as a difference of these two nodes or a combination of these nodes, along the fracture, because of shear slip, it will show a large gradient value, but you need to correct it because the shear slip is already causing some kind of discontinuity, and you cannot consider this discontinuity while calculating the gradient. So how it is being resolved is that it's extended discontinuity DOF or degree of freedom is introduced for this fracture segment correspond to these 4 neighboring nodes, and on each of this fracture segment now we are focusing on the fracture, and we have to introduce some additional basis function there. And here it goes. Here it is how it looks like. Along with this matrix basis functions, we introduce a basis function correspond to the fracture, which has a very nice property. I will show it to you. This basis function has a discontinuity at the fracture line. So at the fracture line, it captures that discontinuity comes up because of shear slip. But there is a very nice property to this basis function is that if we approach the fracture line from both sides of the domain, in the limit of approaching this fracture line, it has a continuous gradient. So that means the gradient on left side is same as here, the gradient on the right side. Sorry, and gradient on the two end of the fractures are similar. So that this particular property helps us now. That means it is we can use the strain calculations more easily here. We do not need to take into consideration now gradient calculation, but at the same time we can take into consideration the discontinuity calculations. Using this particular basis functions, now it is introduced into the system, and now it takes care of the flux calculation on the fractures, on the matrix. And in the fractures, if you remember, we discussed that there is an additional constraint terms comes up, that force is constrained on the fracture, and that constraint equation need to be solved on the fracture along with the divergence equation of stress term in the matrix, and we get a full solution field for displacement for both matrix and fracture domain. Excellent. So how our method compared with respect to some analytical solution? That first need to be checked whether it's really this kind of method works or not by introducing the additional basis function. And in order to check that, we have an analytical solution correspond to a one fracture embedded under the ground, and there is a fixed stress slip solution assumed, and correspond to that slip or shear slip here on the fracture, we need to calculate the displacement solution on the ground here. And analytical solution and the numerical solution, as you can see, approaches the analytical solution as we increases the number of grid resolution. There is always it will not be of course it is if we keep increasing the grid resolution, it will approach the analytical solutions. So this gives us some confidence on our numerical method here that we have used. Okay, so far we have now discussed the mechanics part. So this is how we resolve the mechanics problem. That means we can calculate the shear slip or any force constraint calculation on the fracture. We can resolve it by solving for a stress field and this force constraint using this finite volume method or extended finite volume method that we discussed. Now comes the second part of the problem, which is solve for the flow problem. So there is also a flow along these fractures and in the matrix. So we need to solve for that. Checking my time. Okay, so now the flow solver is our focus. How it looks like is that each fracture is the domain has as I discussed previously, domain has a lot of fractures, but there are a lot of small scale and a lot of large scale fractures. So in modeling the flow problem under this setup, what is being done is that small fractures are approximated as a part of the damaged matrix or porous matrix. That means the matrix domain or rock domain here is assumed to be some kind of porous with some sort of flow going through the system. And the large fractures, the problem is solved for flow problem is extensively solved in the large fracture. So this second equation represents the flow along the large fracture. This typical equation is called Darcy's law. It's typically used in porous media problems, but here it's also could be used in the rock domain problems. So what here I represent is that phi m represent the porosity, local matrix porosity. The PM here represent the pressure gradient, pressure in the matrix. So pressure gradient is needed. And Km represents some sort of permeability, which is if you look into very quickly, it's some kind of how the flow it's an inverse of flow resistance. Sorry, it's a flow resistance actually. How the flow is resisting to the problem, nu by Km. And similarly, along the fracture also, there is additional terms. Here is a PF. Here will now represent the fluid pressure along the fracture, and EF represent the fluid aperture, fracture aperture at the location. Again, going back to our system of numerical simulation, we are not resolving the fractures, all the fractures, but we are assuming some kind of fracture embedded in damage matrix. And this time we do not have the 4 neighboring nodes, but only 1 node. And why this is so? Because this is called staggered grid approximation. That if what we did is that for correspond to each 4 neighboring displacement node, in the center of this we stored the pressure node for the matrix. And when the pressure node is stored in the matrix, so that means correspond to each 4 neighboring grid node, there is 1 pressure node in center that is correspond to matrix. And now when the fracture passes to the same fracture degree of freedom, now correspond to fluid pressure at the fracture location. So now we need to solve for the problem in order to obtain the flux calculations of fluid flow around this matrix segment and flux calculation of fluid flow along the fracture segment. And as I said, there are 4 neighboring grid nodes for displacement solutions also here. So let's focus into how the flow problem is solved. As it's similar to matrix problem for fine volume method applied previously in the calculation of mechanics problem. Just here the system is a little different. Now on this finite volume segment, the equation is again integrated. The equation corresponding to the flow problem is integrated here, and we can use the Gauss divergence criteria to convert the divergence into area integral, as you can see. And now comes to the very interesting point where the numerics applied. This area integral can be converted into some sort of numerical approximation where this gradient on each of the point into area used. And now in order to solve this gradient, and this is where the flux calculation of flow comes up, we need to estimate what is the pressure gradient on each of the segments. So in order to do so, you can use any standard method. Here you can use simple central difference approximation. Here we also need to take care of the neighboring nodes, as I said. So a pressure gradient is a function of pressure difference between the 2 neighboring nodes. This is for matrix. And we, as I said, the north here I represented by this special notations: north, west, north, south, west, and east, which represent the flux calculation in each of this segment. If we look into the fracture, the strategy is more or less same, but now flow is along the fracture, so we have to integrate the equation along the fracture. And here, remember this dimension is 1 less. So for in this simple 2D setup, it is like a line, and we have to integrate the equation along this line to obtain the finite volume solutions. And each of the boundary point here represent the point where the flux calculations are done. So for each of the fracture segment, it need to be calculate the flux on when it is interacting with the next neighboring segment. And in order to do so, we need to know what are the neighboring fluid pressure, and based on that, we can calculate the gradient calculations. So once we know this local segments, we do not know it, but we can calculate the gradient based on that. And this will give us a system of equation. Finally, we come to a system of equation for flow as well as for mechanics, and we solve them using any suitable linear solver algorithms. Usually, because it's a sparse matrix, so what we use is some sort of multigrid approach, which is called which is useful for sparse matrix calculations, and we can use that to solve for the pressure field in this case, for the entire domain, similarly for displacement solution in the other case. So fracture and matrix independently, they have their neighboring nodes, and we can solve for the fluid flow problem independently in each of the cases. But usually the problem is a little bit more complicated than that. What happens is that the problem also have additional terms, and these additional terms are mass transfer between fracture and matrix. So if there is the matrix is completely impermeable, or there is no flow between fracture and matrix, usually this term is not required, but it is not all in the case. The flow, generally the fracture matrix boundaries, there is also mass transfer terms, and this mass transfer term need to be incorporated when you're going to solve for the problem. Otherwise, we're going to have mass accumulation in either fracture or matrix. And also comes the consistency criteria. A simple model for mass transfer term between fracture and matrix is obviously assuming some kind of, it's a function of the pressure difference between fracture and the matrix. But when you're going to model this term, we need to be careful that we are consistent in this approach, because now the fracture and matrix become more strongly coupled, in the sense that these two equations are not independently solvable. These two equations need to be solved together. And in order to solve them together, we need to estimate this flux transfer terms. But if we just estimate this flux transfer term without conserving certain criteria, and very simple criteria is the mass balance, then our system is going to be divergent. So how it's been solved is that mass transfer term between fracture and matrix solved in such a way that the volume integral of this mass transfer in the matrix become equal to the area integral of mass transfer in the fracture. And this will make sure that in an integral sense, we have mass conservation in the problem. So far, we have talked about flow solver and mechanics solver independently. But where this flow and mechanics solver are come together, and why this flow mechanics problem rather than independent, and this is because of the shear failure. There are also tensile opening reason, but I'll first go through the shear failure project. So what happened is that if you consider the domain is only elastic, if the domain can also be poroelastic, where the pressure in the matrix can have a role in the stress calculation, but let's, for the simplicity of the case, assume the domain to be elastic. If the domain is elastic and the fracture, and there is a fluid flow happening in the fracture, there is no coupling between the flow and mechanics. Flow is happening independently. Mechanics is just once we solve for the mechanics problem. But what happened is that, as I discussed before, the flow is creating the pressure, fluid pressure in the fracture, or increasing the fluid pressure. You can do it by injection, like as we discussed, fluid injection can cause some kind of increase of the pressure along the fracture segment. And this increase of the pressure in the fracture segment reduce the compressive force that is applied on the fracture. So you can see, look into it from the interior, there is a force applied, and from the outside there is a compression because of the boundary conditions in the rock. But this interior pressure is reducing the overall or total compression applied on the fracture. And when the compression decreases, it's equivalent to a simple friction problem. Compression decrease means decrease of the normal force that is applied on the fracture. And when the normal force decrease, that maximum friction criteria or maximum friction force also decrease. Friction is static friction into normal force. So if it decreases immediately, so what it lead to is that it is decreasing at some point, it comes to a threshold. The applied shear stress is never going to change because they depend on the boundary condition. So when it comes to the threshold, that applied shear stress now exceed. Now this maximum compression stress, applied shear stress should always be less than maximum compressive stress on the fracture. And if the applied shear stress become equal to maximum compressive stress on the fracture, maximum friction. So I'm a little bit connecting. This tau max represent the maximum compressive stress into friction. So applied stress as shear stress should be less than this. Unless it is less than this, the friction is keeping the contact. Once it exceeds this value, there is a shear slip happen along these fractures. And that shear slip means some mechanical change. The shear slip changes locally the stress concentration around the segment, and it will trigger more and more effect. This is how actually the earthquake happens under the ground. Any change in shear slip will trigger more and more segment to shear slip, and then there is a wave propagation kind of phenomena happen. Here what happened is that pressure is reducing, as I said, pressure is reducing the compressive stress, and an immediate change in the compressive stress is leading to immediate change in the friction. It will lead to a shear slip. The red dot represent a shear slip there. Once the shear slip happens, the neighboring segment getting more stress concentration, and because of shear slip, the hydraulic aperture also increase there. The more fluid will flow out of this segment, and it will lead to more higher pressure in the neighboring segment, and this will create a trigger. So more and more shear slip will keep happening, and more segments are start to fail. This phenomena is well understandable in terms of physics, but numerics is difficult here. Why? Because the flow problem, now we need to, the flow and mechanics problem are more coupled. Every time the flow problem reach this kind of criteria, we need to solve for the mechanics problem. And the problem should be grid and time convergent. And in order to do so, imagine that we have a smaller, so our numerical method is restricted or limited by our grid resolution. So if you are having a smaller grid resolution, we are seeing a faster failure because the small segment fails faster and it triggers faster. So as a result, what happened that if we do not respect a time step in the mechanics, in the flow problem, we get a different solution of the problem for different grid resolution or different time step resolution. So how it is resolved is that CFL kind of criteria used. If you know CFL is a kind of gives you a criteria for wave propagation. So your numerical wave propagation scheme should respect the actual wave propagation scheme. And here, similar to CFL, it's we calculated a time scale dependent on the local grid resolution, and our numerical method should resolve this time scale. Once this time scale is resolved, then we can have a grid convergent solution in this case. Otherwise, the solution will be grid not grid convergent. The more finer grid resolution we go through. So here, look into this time scale, the delta x square. So this time scale is dependent on grid resolution square. So going smaller and smaller grid resolution, the flow time scale reduces. And if we do not respect, if our numerical time scale is okay, it's respect the flow time scale for larger grid, but if we do not change it with this changing flow time scale, then what will happen is that we do not have a grid convergence solution. Alternately, okay, this problem, one critical bottleneck of this problem is now that our time step is grid dependent, and that not just grid square dependent. So that means our computational resource is limited. As we go more finer and finer grid resolution, we need to choose smaller and smaller time step. Involved with that, the linear solver is becoming larger because of the more grid points. So our problem become computationally more expensive. An alternate approach to that is to go into the physics of the problem. And what we did is that in that sense, we checked, or generally it is a notion, or it's a experimentally observed criteria, that friction, whenever there is a small change in the compression on the segments, it doesn't lead to immediate change in the frictional values, maximum frictional value, nu s into sigma minus p. However, it approach this value, new value, over a small time scale, and this time scale is modeling phenomena. Now this time scale, it relaxes to that value. If you use that relaxation value, that the frictional criteria, maximum tau max, is relaxing to this new value over a particular modeling parameter TF, then it's more physically accurate, because now The physics is actually like that. It's not a sharp change. But we need to know what should be the time scale, or how we should be choosing this modeling parameter. So if we choose a correct modeling parameter which respect the time scale of the flow, again, then we can get we do not need to worry about this kind of time step resolution. That means we do not need to worry about that every time we are resolving the grid, we need to have a more finer and finer time step. We just need to respect this modeling timescale parameter. However, choosing this modeling timescale parameter is an uncertainty here, and we need to there is another kind of problem in that regard. So it's a modeling parameter. So with this simple criteria, now just go into some simple problems to show you. There is a center here, a simple large fracture is placed. In the boundaries, the stress conditions are imposed, and in the center, there is a fluid injection well is placed through which fluid is injected into the fracture, and it will, as it is injected into the fracture, it will lead to increased pressure on the fracture. As a result, it will lead to shear failure, and this shear failure will propagate along the fracture. If we just look into the numerical solution, this is how it looks like. Initially, this is called shear slip along the fracture. Initially, with the increasing fluid pressure in the bottom left, you can see it rises, and it's more larger region which become taken over by this shear slip. The right side is a shear stress value. Here you see some kind of fluctuations here, and these fluctuations are a problem in this kind of methods when you applied embedded methods. When you do not resolve the grid properly. However, this will give you computational. It's not a problem because fluctuations are not so high. So that's why we can, for the time being, go along with it. But there are also methods to resolve this kind of fluctuations. And now I will show you that the video where you can see that when you solve the problem without resolving the grid resolution, without respecting the time step criteria, how it's been done. So initially the shear slip is proceeding, and then after some time it's two grid resolution gives two different shear slip solution. So that means here we do not respect the time scale of the flow when you go to the finer grid resolution, and we'll see the different solution for finer and coarser grid resolutions. If we use relaxation, as I discussed, now what will happen is that we have a grid, finer grid solutions and coarser grid solution matches better. Here I will show it further. When we do not respect this kind of relaxation criteria, with increasing grid resolution, we have a separation of the two finer and coarser grid resolution solution. However, if you respect the relaxation criteria, then we have a finer and coarser grid resolutions are approaching more or less same values. Here again, I will skip. So the main takeaway from this part of the project is that the time step should be respected. Time step grid resolution should be respected when you are doing the numerics. Now some examples. Says when we are dealing with fracture network, now I come to the physics a little bit to show how the solutions, what benefit we get from the solutions. Here also, again, injecting on a fracture network, small fracture network. The fluid is injected, and once I run the video, you will see how the shear slip is propagating through the domain. Fluid injection is leading to this red part here, and it will lead to more and more shear slip. And here you can see that shear slip is not uniformly spreading around the domain. Some part which are getting earlier, and some part of the domain spreading later. And the bottom right plot shows a kind of calculation of the earthquake. So every shear slip is an equivalent to a microseismic event, and this event we will not feel it because it is small, but these events could be felt by some kind of special devices that can be implemented there. And these microseismic solutions are very important. This will give us the idea of how, if ever, it will lead to some large scale of seismic activities. Again, within the domain, if we just look in the stress field, because our method also gives the stress solutions within the domain, the stress field is higher and higher stress fields are being seen. as the shear slip propagation is happening, this is the fluid flow, and the shear, there is a more stress concentration in defined part. This stress concentration is causing further shear slip to happen. So it's also an important part to resolve the stress solutions. This simple example shows what is the effect of defined permeability. And by permeability, I mean that if the rock is completely impermeable, then the fluid is mainly propagated through the fracture, and therefore more shear slip happen along the fractures. If the rock become little permeable, then the shear slip under the same time scale shear slip reduces along the fracture, and more, because this is obviously because the flow is mostly going through the matrix, not the fracture. Okay, I'll skip this thing and I'll show this part where this is more complex fracture network. And as you see here, is the fluid flow leading to a lot of shear slips and a lot of microseismic events happening there. But how we can say that our microseismic events are explain the phenomena better? So, one way to understand this is to plot this microseismic phenomena in a semi-log plot, actually, where number of events of the microseismic events, the number of events, this MW is a like what you see regarding earthquakes, like we heard about a Richter scale, like 5 Richter scale, 6. This is a measure of this. So this is basically a measure of a logarithmic measure of the energy released by the system because of shear slip. And whenever we plot this microseismic events, a number of events correspond to a value larger than a particular microseismic event value. For a large points, we get a straight line here in a semi-logarithmic call. It's called Hanken-Kanimori solution. We get a straight line here, and we plotted our solutions for defined grid resolution, and we see that we get a more or less a linear plot here with a particular, we are getting a particular correct gradient or a slope of this plot. Finally, some 3D simulations. So far I showed you some 2D simulation results, which are mostly the fractures are a line in that case, and the matrix domain solved. When you go to the 3D domain, fracture is a plane, and now we have to solve for the fluid flow along those fracture planes and also solve for the mechanics equation. Here I am showing, I will show, there are a number of fractures present in this particular system, but for the timing I'm showing the central fracture there. And when we inject the fluid in this central fracture, it will flow first, propagate through this fracture, it will cause some kind of shear slip there, and then it will taken over by other fractures around. And as I run this thing, you can see that new fractures, whenever this shear slip have a new fracture, I'm showing it in this result. So, and this central plot, top central plot shows the microseismic event because of this shear slip happening. And it's very interesting to see that rather than the central fracture where we are injecting the fluid, some other fractures are taking over the microseismic event. So what is the takeaway from this simulation is that geological structure or geological orientation of the fractures are very important when we're going to do this kind of reservoir operations. What I mean is that if there may be fractures orientation with respect to the boundary conditions define when it's going to fail. So if it's very nicely oriented, strongly oriented with respect to the boundary condition, it is more stronger. Means it is more stronger in the sense that there is no shear slip happening much. But there may be 1 or 2 fractures which are weakly oriented. Like if there is something called San Andreas fault in California, which is a fracture around which, or large fault around which large scale shear slip happen. Similarly, in our country also, there are weakly oriented probably shear slip or fracture plane available underground, like for example in high seismic zones. So those faults or fractures gonna fail faster. So similarly, when you're gonna do a fluid injection process in such an underground, the first thing is that we need to know what is the geological orientation of the system, and we need to have a better understanding to predict or to understand what is the kind of seismic event that it can lead to. I think do I have time or hello?
Okay, Rajni, you can continue.
I can continue. Okay. Now I'm coming to another aspect of the problem, which is called tensile opening. So we discussed so far the shear opening, and then there is another phenomenon which is called tensile opening. So what happened in tensile opening is that this time the fluid injection, the fluid pressure is very high, and this will directly lead to, unless the external compressive stress is higher than the internal fluid pressure, the fracture is fixed, it is not opening up. But once it exceeds, the fracture itself naturally opens up, because the fluid pressure has put so much higher force on the fracture that it opens against the external compressive stress. So tensile, this is called tensile opening, and modeling this tensile opening creates an additional complexity. Now within the fracture there is a more stronger flow and mechanics coupling. So why? Because every fracture segment which fails, it is failing because of local fluid pressure. By fail, I means here the tensile opening. I should say opens. So every fracture that opens, it is because of the local fluid pressure now, and local stress condition define this. And every time a fracture open, it lead to change in the local condition for aperture, fluid aperture, and this plays a role in the calculations of fluid flow problem again. The similar role is also applied in the shear slip case, but there the mainly its role is governed in the permeability calculation because the change is small. But here the volume of the system itself changes. So it is seen by this term dSn dt. So locally fluid opening lead to more volume and therefore fluid problem. So this is a more strongly coupled problem in the fracture. So we cannot just solve the problem in the flow and see the pressure and just change it, update it in the mechanics. We need to do it in an iterative way or in a coupled way. One approach, of course, to solve everything together, stress problem, flow problem, and this local conditions together. That will be computationally more costly because this will be coupled problem. Another approach is called segregated solution, segregated solver, iterative solver, where we solve each of them separately. First we solve maybe for the flow problem, and then we update the mechanics problem, but we do not update the mechanics problem just directly. We need to do a local iteration unless flow and mechanics doesn't affect each other solution. Till then we keep solving the problem, and once this happens, then we go to the next time step. So if you look into here, we just go simply to the case. If you look into the finite volume approximation here, the same we do the integrated solutions for the flow problem, integrated solution local integratedly local pressure field is equal to the stress, compressive stress, and for the mechanics problem. And now if we now the question is how we go to the next step. So if you see in the flow problem, there's dSn term. In this Sn is dependent on solving this second term. What we can do directly is that we use the previous iteration solution for Sn while we calculate the pressure problem. And then this will be called fixed strain approach. Why? Because displacement of the strain is fixed over an iterative time step. Iterative step. However, numerical calculations have shown, and numerical stability analysis have shown that this approach is not, what should I say? This approach is more stable. Means it will become unstable with time. So that means numerical solver is not stable here. So a better approach is used, which is called fixed stress approach. And what is done in there is that over an iteration step, the strain is updated in such a way that local stress is fixed, or some sort of volumetric stress is fixed, and there is a numerical stability analysis is performed for that. I also did it in my paper. I will share it in the end. And there we have seen that if we choose this particular coefficient in such a way that local and grid resolution is respected, then again we can have a converged iterative solution in this case. And so we have a converged solution for tensile opening. Here we show the grid converged solution with this particular approach. Again, external finite volume method combined with the finite volume of the flow problem, and it's also important to show that our problem is independent of coefficient unless we respect that particular criteria, L by Cp. So again, takeaway from this particular segment is that when we do the flow mechanics coupling, and particularly if we do the iteration there, we need to be careful about what is the iteration procedure we need to choose. Otherwise, we can get a numerically unstable solution. Finally, I will conclude my topic. So I have discussed an approach called extended finite volume method without resolving the grid, try to solve the fluid flow and mechanics problem in the fractures and matrix domain. We discussed about a flow solver where a consistent flow mass time scale. First of all, finite volume method is used for solving the flow problem. And also when the flow in the flow problem, the fractures and matrix are coupled, we need to solve for that using a consistent mass transfer term modeling. Shear strength, again, we saw that it's very important to resolve the time scale when we go for shear slip problem. In this case, flow and mechanics are both coupled, and we need to solve for the time scale. So in order to solve for the time scale problem, we need to respect the certain kind of flow time scale while we do our numerics. And finally, this fixed stress approach, as we discussed now. So where we need to respect when we do iteration in the strong flow mechanics coupled problem, we need to do it in such a way that fixed stress criteria is resolved. Method also have some limitations. So far, we solve for only for the mechanical equilibrium problem. So that means earthquake dynamics are not solved, and earthquake dynamics also has a role. As you know, earthquake is a wave propagation problem, but because in this case the problem is small scale, we didn't solve for wave propagation. But if we want to extend it to large scale earthquake solutions, earthquake problems in a more geological setup, then we need to solve for wave propagation cases. Another important fact is that fractures are only solved along the pre-existing line, but change in fractures or opening of fractures are causing stress concentration in the fracture tips, which create more cracks in the fractures. And these cracks are also required to be solved. That there is a new fracture created completely in the domain. There are many approaches called J integral used in finite element concept. We are working on this direction and see how we can resolve that particular problem. More better friction laws can be used. Here we use simple percussion friction law, but there are more advanced friction laws called slip weakening friction law, where not just shear slip, but shear slip rate also have a dependence on the friction calculations. And finally, more realistic test case we are going to solve. We are still trying to find out that if we can resolve more proper test case, which is realistic in oil and gas field or geothermal solutions, etc. Thank you so much for your attention, and I'd be happy to take up any question that you have.
If you have any question, please write in message box or just unmute the button. Dear participants, if you have any question, just unmute the mic or write in the message box.
Thank you, Dr. Deg, for a very interesting and stimulating presentation. I just had one question. Am I audible?
Yeah, sure.
Yeah. Now, I, of course, not know much about your area. I'm only a layman. But since you are talking about seismic activity, I'm just asking. Actually, I don't know much about Switzerland and earthquakes or anything occurring over there. But in Italy, I think there are several very interesting, volcanic eruptions and earthquakes taking place from time to time. Yes. So, do you use that as data for your investigation?
Yeah. So Italy's earthquake, yeah, it's a concern. But as I said, one defines that is that these earthquakes are because of large-scale geological processes, means volcanic eruption and plate tectonics and all. And there, as I said, the wave propagation still need to be modeled. This is not because of industrial applications. So that's why our model immediately cannot be applicable to that large scale, because there it's a wave propagation or this acceleration term that I showed that also played a very important role. So we have to update, or we are working on it to take it to the next level.
Okay. Thank you. Thank you, sir.
Rajdeep, I have one question.
Yeah, sure.
What is the solver for the sparse matrix or sparse matrix? Which matrix solver you are using?
Oh yeah, so it's an elliptic problem for particularly for the mechanics and also for the flow approximate, not elliptic but yeah, parabolic elliptic. So what we do is that we use a multi-grid. It's called Trilinos. You know Trilinos? Heard about it? As a method, we use this Trilinos solver, but it's a means in a very simple way. You can also solve this using some Gauss-Seidel iterations, but it will be like a iteration will take a lot of time. So what we use, it's called multi-grid solvers in Trilinos.
Okay.
Which we do not solve directly, but we use a software there in that case to solve for the linear solver.
What is the CFL condition?
Here CFL condition, as I said, is not directly applicable because for CFL condition you need explicit time step, but here we have an implicit time steps for flow problem. So in the flow problem itself is it's always we are solving for an large matrix solution for the pressure at next time. So it's an implicitly. So that's why in the flow problem we can use a large time step. However, because flow and mechanics are coupled, there is another condition as I saw comes up, because every time the flow propagation happen, it lead to mechanical failure, and there we had to respect this particular criteria by choosing a time step which is dependent on the grid's square term, actually delta x square. So that I showed in that. I can show it again. So let me show it. Yeah. So can you see my screen now?
Okay.
Yeah. So here you see this delta x flow. This particular calculation is taken purely from the parameters of the problem. Yeah, here you can also do more mathematics. You can look into it, but we have, from an engineering sense, we use the simple mechanical parameters, and based on that we calculated what will be the corresponding governing flow time scale for the depend on particular grid resolution. And when we have this flow time scale, our numerical time step should resolve this particular flow time scale. So that's why we see here a grid square dependent numerical time scale.
So it is second order conversion in space.
Yeah, second order convergence. Yeah.
For time?
Yeah, for time also, time is first order convergence. Yeah, time is first order because we used backward Euler here, simple backward Euler, but we can go for more complicated case like Crank-Nicholson and all. But here we are using backward Euler case simply.
And you have used central difference approximation for the numerical.
Yeah, exactly.
But you can use one-sided second order scheme, or your numerical scheme one-sided, or
yeah, I use central difference, but one-sided second order scheme can be used also here, I think, depend on the flow condition. But because, as I said, implicit solver we are using, so so I think it will not have a much difference actually. If you are respecting the CFL criteria that you are talking about, then probably we need to have a one-sided schemes, upwinded direction schemes. But since explicitly, if you're gonna solve. But if we're solving implicitly, then we can use central difference here.
Thank you, Rajdeep.
Thanks.
Thank you, Rajdeep, for your wonderful presentation. We have learned so many things from your presentation. We have learned finite volume method and the basics of finite computational fluid mechanics problem in fracture domain. We have learned how to use numerical simulation without resolving the grid around the fractured area. Also, we have learned how to use the extended finite volume with fluid mechanics grappling and the role of friction and microseismic activity due to reservoir activities. Thank you, Rajdeep.
Thank you so much. Thank you very much.
Now, so, I request to IB sir to hand over the memento to Dr. Rajdeep. Rajdeep, please
Yeah.
close your presentation.
Yeah. Hello. Yeah.
Anup sir, please. Yeah. So thank you so much, sir.
Thank you so much. That looks so nice. Yeah.
In this pandemic situation, this is the only alternative in our hands. So you please accept a small token of appreciation from us, and we will send it to you through our email. So this is
Thank you.
a key memento. This is from our side on behalf of our department as well, Guru Nanak Institute of Technology. Just you please,
Thank you.
we will be very happy if you will accept it.
Yeah, thank you, ma'am, so much, and that's very nice. Like, thank you for doing this and giving me this opportunity to present the work. And yeah, surely, yeah, thank you very much for always. It's my pleasure to present in your institute.
Thank you, sir. Hope in future we will listen from you again.
Sure.
Thank you. Thank you.
Thank you very much. Okay. Then.
So
See you.
with this, yeah, thank you.
Yeah.
With this, I'm declaring the closing of the session. So hope you have enjoyed a lot. Thank you so much. Thank you, everyone who have organized this webinar. Thank you, Moinak sir, Dr. Moinak Devnath, for this preparing this memento. Thank you. Thank you so much.
Okay.
So
Bye
here,
bye.
I'd request Anup sir to please close the session. Thank you, sir. Thank you all.
Thank you, Rajdeep, for your
Anna.
nice presentation and accepting our invitation. Okay. Thank you, Rajdeep.
Bye bye. Bye.
Bye.
Thanks.